We've spent years fighting catastrophic forgetting in the parameter space, struggling with replay buffers and elastic weight consolidation just to safely update theta without nuking the representation space. Today on the YouTube series AI Paper Slop, we're covering a paper that ignores theta entirely. It is titled Harness Continual Learning, Continual Adaptation Beyond Model Parameters. This is from Bori Kang and a team out of Nanjing University and the University of Wollongong. And the premise is radical. You keep the foundation model 100% frozen.
Right.
All the learning happens purely in an evolving external harness.
Yeah.
But there is a massive catch. As these agents adapt their prompts, their memories, and tool use policies to solve new tasks, they suffer from a new phenomenon called harness-level forgetting, where fixing a new workflow accidentally breaks an old one. So to solve this, the paper introduces a guarded harness evolution framework.
Right.
A continual optimizer proposes updates, and a continual evaluator strictly tests them against a historical anchor set before committing them to the agent's state.
Which is exactly why this matters to anyone deploying agents in production right now. We're looking at mathematical proof that you can explicitly control the stability-plasticity trade-off completely outside the neural network.
Yeah.
This framework theoretically allows agents to, acquire an infinite number of skills and autonomously recover from execution failures without ever requiring a single gradient update.
Or spinning up an expensive retraining run.
Exactly. No retraining runs.
Okay, let's unpack this because it's a total paradigm shift. For the longest time, the industry standard for continual learning has been, it's been model-centric.
Mm-hmm.
If an agent fails a task, the knee-jerk reaction is to fine-tune.
Right.
We collect the failure trajectories, build a data set, run LoRa or full parameter tuning. But keeping the foundation model entirely frozen is basically it's like keeping a car's engine completely untouched, but dynamically upgrading the navigation system, swapping the tires, and rewriting the driver's manual on the fly based on the terrain.
That analogy actually holds up perfectly, especially when you consider what an agent actually is at runtime these days.
Right.
The transition from standalone LLMs to agentic systems means the model is now basically just a stateless reasoning engine.
Yeah, just the compute.
Exactly. The prompts, the JSON schemas for tool calling, the routing logic, these aren't just lightweight wrappers anymore.
Yeah.
They constitute the actual state of the system.
Right, the architecture.
Yeah. When an agent learns to query a complex internal SQL database or handle a new multi-hop reasoning constraint, that acquired knowledge is stored in the harness, not the weights.
Right, because the weights are frozen.
Right. So we have to treat that external architecture with the exact same rigorous acquisition and retention constraints that we historically applied to the neural network itself.
Right. But if we're treating the harness as a mutable, evolving state, which the paper denotes as H-N at interaction step-in, we really need to get into the weeds of what actually inside it. Because my immediate pushback, just as an engineer, is that if your prompts, your arg retrievals, and your routing logic are all constantly changing dynamically based on execution feedback, you're looking at an infinite search space.
It's massive, yeah.
How does this not just collapse into a chaotic mess of moving variables?
Well, it would collapse if they just let the LLM rewrite its own code base haphazardly.
Right.
But instead, they structure HEN into 4 tightly coupled, jointly versioned pillars.
Okay.
The first is the task interface, or IN. You can think of this as the normalization layer.
Okay, so what does it do?
It takes raw, chaotic inputs, whether that's a messy user prompt, raw image pixels, or just environment observations, and parses them into a structured representation that defines the objective and the constraints for the router.
So it's essentially the formatting parser that standardizes the real world into a payload the rest of the harness can actually digest?
Precisely, but it's an evolving parser.
Ah.
Then you have the second pillar, the experience memory, MN, which is arguably the most critical for retention.
The memory, right?
And this is split. You have raw memory, which is your standard episodic buffer, like concrete records of inputs, execution trajectories, reward signals.
Sure, standard stuff.
But the real heavy lifting happens in the abstract memory. Here, the framework uses the LLM to summarize those raw trajectories into high-level, reusable guidance.
Wait, let's drill into that for a second. How is it actually summarizing?
Yeah.
Are we talking about generating a textual string of lessons learned? Or is it creating structured key value pairs for semantic search? Because if you just dump raw text into a vector database, the retrieval accuracy is going to degrade as the memory bloats.
No, it's generating structured guidance.
Okay.
When a task succeeds or fails, The model extracts the specific causal pattern.
Like what?
For example, if it failed because it tried to pass a natural language state into an API that requires an ISO 8601 timestamp.
Oh, right.
The abstract memory codifies that specific constraint,
I-
and that abstraction feeds directly into the third pillar, which is the capability map, CAN.
The toolkit.
Yes. The capability map houses outer capabilities, so your standard external APIs, OCR endpoints, calculators, things like that.
Right.
But more importantly, it houses inner capability.
Inner capabilities, okay.
The agent actually takes the explicit procedures codified in the abstract memory and formalizes them into reusable, executable skills.
Wait, really? So if it figures out a complex sequence of API calls to solve a specific data parsing issue, it essentially abstracts that into a new Python function with defined inputs and outputs and just adds it to its own library.
It does, yeah.
It's writing its own functions over time.
Exactly. It turns accumulated semantic knowledge into parameterized tools.
Wow.
And finally, you have the adaptive router, RNM. This is the conductor.
Okay, the router.
It takes the normalized input from the task interface, retrieves the relevant semantic context from the experience memory, maps that to the right tools in the capability map, and constructs the final execution prompt for the foundation model.
Okay, and here's where it gets really interesting. Because all four of these pillars are versioned together as a single state space.
Yes.
Which means changing one component to solve a new error can completely sabotage an old solution.
Yep.
It's the classic stability plasticity dilemma, but lifted out of the gradient space and dropped right into the runtime architecture.
That is the core threat they identify, harness level forgetting.
Right.
In neural networks, updating weights to minimize loss on task B might destroy the representations that solve task A.
Catastrophic forgetting.
Exactly.
Yeah.
In an agentic harness, the dependencies are just as fragile, but they're semantic.
It's exactly like dealing with technical debt in a legacy microservices architecture.
It really is.
Like, let's say you get an error where the agent is failing a complex multi-hop reasoning task. So the system updates a routing prompt in the adaptive router to enforce deeper chain of thought logic. And it passes the new task brilliantly. But because you changed the structural expectations of the router, it suddenly fails to retrieve the correct JSON schema for a basic calculator tool that it learned to use flawlessly just yesterday.
Which is terrifying from a deployment perspective.
Absolutely.
A previously solved query suddenly throws a parsing error. The foundation model hasn't changed a single parameter, and the failure is entirely driven by a cascading semantic shift in the harness state.
Yeah.
Like, an update to the task interface might subtly alter a constraint format, causing the router to hallucinate an argument when calling an inner capability.
Right.
You've introduced regression bugs without ever touching the code or the weights.
So we obviously can't trust the agent to just endlessly mutate its own harness unchecked. What is the actual cure they propose?
The cure is guarded harness evolution.
Okay.
It fundamentally separates the generation of an update from the commitment of that update.
Like a PR review process.
Kind of, yeah. It runs a strict proposal evaluation loop. It starts with the continual optimizer. When the agent receives post-execution feedback, like an environment reward or a compiler error, the optimizer generates a localized candidate harness, HN+1.
By localized, I assume it's constraining the search space? Like it can't try to mutate all four pillars simultaneously?
Correct. It modifies one targeted component at a time while holding the others fixed.
Okay, that makes sense.
It might generate K different variations of a new memory abstraction or a new routing rule.
Mm-hmm.
But generating those candidates is just the first step.
Right.
They then have to pass through the continual evaluator, which acts as the ultimate gatekeeper.
Right, so it doesn't just push the prompt to production because it solved the immediate error.
No, not at all. It forces the candidate through 3 strict checks.
Okay, what are they?
First is current improvement. The new harness must improve the validation score on the current task by a predefined margin, delta N.
Okay,
If it doesn't meaningfully move the needle on the active problem, it's immediately discarded.
makes sense.
Second is validity. The updated harness must still produce legal tool calls, respect syntax schemas, avoid formatting hallucinations, all of that.
Basic sanity checks.
Exactly. But the third check is the historical retention check, which is really the crux of the continual learning aspect.
Oh.
The evaluator tests the candidate against a stored anchor set of previously solved tasks.
Oh, boy.
The loss on this anchor set has to fall under a specific tolerance budget, BAEN. If the new prompt breaks too many historical tasks, it gets rejected, no matter how perfectly it solved the new one.
Okay, I have to jump in and push back on this.
All right.
As an ML engineer, the moment I hear we rerun a historical anchor set during runtime evaluation, warning lights just go off regarding latency and token compute costs.
Oh, sure.
We're already dealing with massive KV cache overheads in agentic workflows. Running historical anchor sets for every single proposed prompt tweak or memory update sounds incredibly token-heavy. Are we seriously burning millions of tokens in a simulated CI/CD pipeline just to check if a prompt tweak broke a calculator?
Look, that is the most common bottleneck with any replay-based mechanism, whether you're doing experience replay in RL or this kind of harness evaluation.
Right.
But the paper addresses this by strictly bounding the anchor set, AN. It is not an ever-expanding database of every interaction.
Wait, bounded how? Because if I have an agent running autonomously for 6 months, that anchor set is going to bloat regardless of how selective you are initially. How are they pruning it to maintain inference speed?
It uses a fixed capacity reservoir sampling approach.
Okay.
And is balanced by a predefined ratio of historical successes and failures. When the anchor set hits its maximum capacity, which is kept relatively small, it aggressively prunes older redundant examples while ensuring high-density representation of edge cases.
Ah, I see.
You're intentionally trading inference compute during the adaptation phase to guarantee strict stability in the deployed state.
Right.
Yes, it costs more tokens to evaluate the update, but it prevents the catastrophic downstream cost of an agent breaking its own core functionalities in production.
Okay, that makes sense. You treat the evaluation cost as the price of reliability.
Exactly.
So let's look at the empirical evidence. The Minecraft experiments really stand out here because embodied environments are notoriously unforgiving.
Oh, extremely.
If you forget how to craft a pickaxe, you can't mine iron, which means the whole tech tree collapses.
Yeah, the Minecraft curriculum is basically the ultimate stress test for state retention and capability accumulation.
Yeah.
They took a frozen Quinn 3.627b model and dropped it into a 50-task sequential curriculum.
50 tasks.
Yeah, we're talking progression from basic wood gathering to complex multi-step dependencies like smelting iron and crafting redstone logic.
So the baseline results are exactly what you'd expect. An agent with a static harness, just standard fixed prompting with no continual updates, hits a hard wall at 15 tasks.
Right.
It simply lacks the semantic memory to navigate the deeper dependencies. But the agent using Harness Continual Learning, or HCL, completes all 50 tasks.
All 50. And what we should really focus on is the execution efficiency.
Right, the action count.
Yeah, completing the tasks is one thing, but the HCL agent finished the full 50-task curriculum using only 83 cumulative environment actions.
Wow.
When they tested dynamic memory management baselines like memRL and mempy within the same environment, those agents required 88 and 91 actions, respectively.
So fewer actions means less redundant execution.
Exactly.
The HCL agent isn't thrashing. It isn't stuck in infinite loops trying to recraft tools it already has in its inventory because its memory and capabilities are versioned and protected by that gatekeeper. It actually trusts its own state.
And that trust is mathematically enforced. To really see how that enforcement works under the hood, we need to look at the textual reasoning and multimodal perception experiments.
Okay.
This is where they isolate that BN parameter, the historical loss tolerance budget,
Yeah.
and show exactly how it dictates the behavior of the agent.
Right. This is where we dial the knobs on stability versus plasticity.
Yes.
For the textual streams, they ran the framework through music for multi-hop reasoning, Proofwriter for logical deduction, and GSM8K for math. They used DeepSeek V4 Flash, again, completely frozen, and they tested two extreme profiles, stability HCL and plasticity HCL.
Let us define the boundary conditions there. Stability HCL sets BN equal to 0. Zero historical loss allowed. If an update breaks even a single previously solved anchor task, the evaluator rejects it. Period. Plasticity HCL, on the other hand, sets BN to infinity.
Okay.
It allows unlimited historical loss. As long as a proposed update improves the current task and is syntactically valid, it gets committed to the harness.
So the numbers beautifully illustrate the trade-off. In the textual sweep, moving from BN equals 0 to BN equals infinity increased average, forgetting from 0.39 to 3.45.
Yeah.
Plasticity HCL naturally forgets more because it's aggressively overfitting to the newest task feedback.
But the intuitive assumption most engineers would make is that allowing maximum plasticity would eventually result in the highest overall performance.
Because the agent is completely unconstrained in how it adapts to new data, right?
Exactly.
But that assumption is dead wrong here.
It is.
And this is really the aha moment of the paper. A moderate value, specifically setting Bn equal to 1, meaning you allow at most one historical anchor to fail per update, actually yielded the highest final average performance across the stream.
Yeah.
It hit 63.46%. It beat Bn equals infinity.
Which proves that unconstrained updates eventually cannibalize the harness.
Yeah.
If you set Bn to infinity, a locally beneficial prompt tweak for today's math problem might casually overwrite a generalized routing rule that you're going to desperately need for tomorrow's logic puzzle.
Right.
By enforcing a strict but non-zero historical retention check, you force the continual optimizer to find solutions that generalize across the task distribution.
It functions exactly like a regularization penalty or like an early stopping mechanism in traditional neural network training.
That is exactly it.
In standard training, if you optimize purely for the current batch without a regularization term, the weights overfit and validation loss spikes. Here, Bn equals 1 acts as a semantic regularization term. It forces the LLM to write prompts and tools that solve the new problem without increasing the semantic loss on the historical distribution. That is incredibly elegant.
It really is. It maps the fundamental principles of gradient optimization perfectly into the discrete token space.
Wow.
And they proved this isn't just a quirk of text processing either.
Mm-hmm.
In the multimodal stream, using Qwen 3.627b on COCO and RefCOCO datasets, the agent had to constantly shift spatial reasoning strategies between object detection, visual grounding, and captioning.
So a lot of context switching.
A ton of it.
Huh.
Both HCL profiles substantially outperformed the zero-shot baselines and dynamic gradient methods.
Yeah.
And again, Stability HCL maintained the lowest forgetting at 0.22.
Okay.
The Bn threshold is a universal control dial, regardless of the modality.
So what does this all mean when we break it down to its component parts? We know the framework works, but which pillars of the harness are actually doing the heavy lifting?
Right.
Let's look at the ablation study they ran on Qwen 3.54b to isolate the variables.
So the ablations really validate the architecture's design. They took the full HCL setup and systematically froze updates to one component at a time, leaving the rest adaptive.
Okay.
When they disabled updates to the task interface, or disabled the experience memory, they saw massive, catastrophic drops in final performance.
The memory drop is the one that really stands out. When they turned off memory updates, forgetting spiked all the way up to 0.83.
Because it proves a crucial architectural reality. Memory isn't just a scratch pad for context injection. It is the fundamental semantic anchor for retaining old behavior.
Oh, that makes sense.
If the agent cannot continuously update its abstract and raw memories, the adaptive router becomes effectively blind.
Yeah.
It has access to tools in the capability map, sure, but it loses the contextual grounding required to know when to execute them as the environment shifts.
It's like trying to traverse a maze, hitting a dead end, and being physically unable to remember which turn you took. You're mathematically doomed to repeat the exact same failed trajectory. Interestingly, disabling updates to the capability map or the adaptive router caused smaller performance drops in the multimodal stream.
Right.
But that makes sense, as visual question answering relies slightly less on long-horizon executable procedures than something like the Minecraft curriculum.
Yeah, the dependency weighting between the components scales with the complexity and horizon of the environment.
Right.
But if we synthesize the ultimate value proposition for ML engineers, HCL proves that a single, completely frozen foundation model can continually handle highly heterogeneous tasks, from multi-hop math to open-world survival,
Yeah.
while maintaining a mathematically controllable, transparent balance between adaptation and retention.
It is a total paradigm shift. Which leads me to a really provocative thought to close us out here.
Okay, let's hear it.
If the agent's harness is doing all the actual learning, and it's doing it this effectively, and the multi-billion parameter model weights remain completely frozen, acting just as an inference engine,
Yeah.
will foundation models eventually become standardized, interchangeable commodities?
Oh, man. It's as the logical endpoint of pushing state into the harness.
Right.
Think about how we treat CPUs. You don't rewrite the silicon architecture of your Intel or AMD chip when you install new software.
No.
The CPU is a generalized processing commodity. The intelligence, the unique behavior, and the state of your machine live entirely in the software, the RAM, and the file system.
Right. So in 2 or 3 years, maybe nobody at the enterprise level cares if you're hitting an API for Qwen or DeepSeek or Llama under the hood.
They will.
They're all just standardized logic processors. The true intellectual property, the actual enterprise value of an AI system, won't reside in a proprietary checkpoint of weights.
No.
It will reside entirely in the uniquely evolved, highly customized harness state. Your competitive advantage will be your dynamically curated abstract memory and capability map that has spent 2 years evolving, running billions of execution loops without catastrophic forgetting.
It fundamentally redefines where the intelligence in artificial intelligence actually resides.
It really does.
It is no longer embedded in static parameter tensors. It's alive in the architecture surrounding them.
We used to think we could just point to a cluster of neural weights and say, well, there it is, that's where the knowledge lives.
Yeah.
But this paper shows us that the weights are just the engine block. The actual muscle, the memory, and the skill of the system are living entirely outside the model, adapting in the harness. Something to mull over as you build your next agentic workflow. Keep your models frozen and your harnesses evolving.